Functional analysis. Functional analysis is an abstract branch of mathematics that originated from classical analysis. Its impetus came from linear algebra, ordinary and partial differential equation, approximation theory, linear integral equation, etc., whose theory had a great effect on the motivation and development of the new ideas. In functional analysis, we deal normally with the abstract space, and we use the abstract approach in connection with the abstract spaces. The abstract space we mean a set of unspecified shape point together with some axioms defined on it. Now, when these axioms are changed, then corresponding the structure are changed. For example, if we take a set X with the two operation addition and scalar multiplication, and X is over a set field, say real or complex number, then this will form a structure, and we know this structure is a vector space or linear space, provided with addition and scalar multiplication this satisfies some conditions. See, when we take X set of points X and introduce the notion of the distance d on it, satisfying a certain condition, then this new structure we call it as a metric space and denote it as xd or x. When the idea of the length of the vector is generalized to an arbitrary set X, then this gives a concept of the norm space X norm, and a complete norm space we have a called a Banach space. So, idea of the norm space and Banach space can be introduced. Then further, the scalar product which is available in the three dimensional plane R3, the dot product or scalar triple product, when it generalized to an arbitrary set X, where arbitrary vector space X, then we get a new concept, this we called a inner product space or a complete inner product space, we call it as a Hilbert space. So, basically with the help of the various structures defined on a set X or on a vector space X, we get the various types of the structures like a vector space, metric space, norm space, Banach space and Hilbert space. In this particular course, we will deal in detail the concepts of metric space, their related results, norm space, Banach space, dual spaces, set of all boundary linear functional defined on this, and then inner product space, Hilbert space. There are few results which we call it as a fundamental theorems of functional analysis. Those theorems will also be discussed, which will be used very frequently in the development of the theory of the functional analysis. So, we will start with this today lecture on metric space. So, before starting this definition of the metric space, let us see the motivation behind it. In calculus, we study the functions defined on the real line R, and during this study of the functions, we also go through the concept of the limits. When we say the limit of the sequence x n is x when n tends to infinity, the meaning is that when difference between x n and x is very close when n is sufficiently large, or x n is approaching to x when n is sufficiently large, when n tends to infinity. What do you mean by this? It means we are using basically the idea of the distance function on a real line, because if I take this as x and these are the points x1, x2, xn, which are tending to x as n is tending to 0 infinity, it means the difference between x and xn, this difference is coming closer as n is approaching to infinity. Now, this difference, absolute difference between the 2 points is nothing but the usual notion of the distance over the real line. Okay. Now, this particular type of the distance function, which is defined over a real line, satisfy certain conditions. It's always be greater than equal to 0. It cannot be negative. It's a real quantity and finite. So, if we take the 2 point x by let it be on the real line, then mod of x minus by will always be greater than equal to 0. It's real and finite number. So, it's a real finite non-negative number. It can be 0 at the most when x is equal to y and vice versa. Then whether we measure the distance from x to y or from y to x, the distance remains the same. That is, this is d symmetric in x by. Then the another property which modulus function enjoy is that if I choose a point z on the real line either in between x by or maybe outside of this, then x minus z will always be less than equal to mod of x minus y plus y minus z. This property we also call it as a triangular property. Triangular property. Why? Because we know in case of the triangle, if we add the two sides, then sum of the two sides can never be less than the third side. That is, distance from x to y plus y to z will always be greater than equal to distance from x to z. So, that is why it is called the triangular inequality or triangular property. Now, keeping in mind this definition, these conditions which the usual metric function on the real line enjoy, we wanted to extend this idea on a general abstract set x. Why should we restrict our study only on the real line or only on the complex plane? Let us take x be an arbitrary set where the elements may be a set of real numbers, elements may be a complex number or elements may be functions. It may be bounded function, even it may be an infinite sequence like this. So, when we replace this set of real number by an arbitrary set of points, then the question arises how to define the notion of the distance between the 2 points of that set, and this leads to the concept of the metric space. Okay. So, we now define the concept or definition of a metric space as follows. A metric space is a pair x d where x is a set and D is a metric on X. Basically, we say D is a, so in fact, D is a function from x cross x to R 0 set of non-negative real number such that for all x by z belonging to x, we have number 1, the function d is real valued, finite and non-negative. That is d of x, that is d x by will always be greater than equal to 0 for all x and y belongs to x, for any x y belongs to x. So, it will always be greater than equal to 0, it is a non-negative quantity, finite and real valued. Second, d of x by is 0 if and only if x is equal to y. And third, d of x by equal to d of y x, that is d is a symmetric function with respect to x and y. So, symmetric or symmetry is there. And last property, that is the triangular inequality, is d of x by is less than equal to d of x z plus d of z y, where x by z are the points in capital X, and this property is known as the triangle inequality. Okay, triangle inequality. Clear? So, what we see here is that we have taking the idea of the usual notion of the distance function on the real line and generalize that idea to an arbitrary set x, so that any 2 point of that set, if it satisfies these 4 conditions, then we say the set x together with the function d forms a metric space. Okay. So, the pair x d is a metric, hence x d is a metric space. Or so this x d is a metric space. Clear? Now, this triangular inequality which we have mentioned can be generalized to endpoints also. Suppose we have x 1, x 2, x n many point and we want to find x by, then this can be written as x 1 plus d of x 1 x 2 and so on, say up to d of x n y. So, this idea can be generalized in general. Okay. So, that will be sometimes used for this. Okay. Now, let us see few examples which based on this definition to justify whether this metric space or not. Example of the metric spaces. Metric space. Very simple example of a metric space, we know the real line R with the metric D defined on this. So, let x be the set of all real numbers and notion of the distance d is defined as mod of x minus y, where x and y are real. Then as we have seen earlier also that this satisfy all the 4 conditions of the metric space, hence this R under this D metric is a metric space. It is easy to prove okay, because this is already we discussed. If we take the Euclidean space, R 2, the R 2 is the set of, let X be the taken as set of all ordered pairs, set of ordered pairs of real numbers, ordered pairs of real number. Say for example, X, which is xi1, xi2, xi's are real, then this set of pair which is in the R 2 space, if we introduce the notion of the distance R 2 as d of x comma y is square root of xi1 minus eta 1 whole square plus xi2 minus eta 2 whole square, where x is xi1, xi2, y is eta 1, eta 2, both are point in R 2. So, this is our space X, which is R 2 space, okay, R 2 space. Then this notion of the distance which define this forms a metric space. Why? Because D, which is defined in this fashion, will be a non-negative quantity because of the square and square root. Then it is real, finite and non-negative. If dxy is 0, then sum of the two non-negative quantities is 0 only when individually the terms are 0. So, xi1 is eta 1, xi2 is eta 2, and we get x equal to y, and vice versa. If x equal to y, d of x y will be 0. Then d of x y is the same as d of y x, which is obviously true because of the square. If I interchange xi1 eta 1 all xi2 eta 2, it will not affect the whole thing, and we get the d x y is the same as d of y x. The fourth property, M4, that is the triangular inequality, requires some more inequalities, some more concepts to prove the triangular inequality follows. So, that particular concept or inequality we call it as the Minkowski inequality. So, that will be derived later on, and with the help of the Minkowski inequality, it can easily be shown that it satisfies the triangle inequality. Okay. So, time being we will just assume that this satisfies the triangular inequality. Hence, all the 4 conditions of this D function satisfied. Therefore, this space R2 under D forms a metric space, and this we call it as a Euclidean metric space or Euclidean space. Okay. The parallel to this, we have the unitary space or complex number. Okay. The unitary space, when the points are complex number, then we get unitary space. So, we generalize this thing and we get Euclidean space R n and unitary space C n. When n is 1, we get the C. Okay. C is a point. So, for n is equal to 1, C is the complex plane. C is the complex plane. Okay. So, what is our R n C n? R n is basically the set of all n tuples xi1, xi2, xin, where xi's are real. Xi's are reals, and Cn is the set of all, say, Z1, let it be here say Z, Z1, Z2, Zn, where Zi's are complex numbers. Okay. Now, we want to introduce the notion of the distance on this. So, on Rn, we introduce the notion of the distance dx by h under root of xi1 minus eta 1 whole square, xi2 minus eta 2 whole square minus xin minus eta n whole square. And on Cn, we introduce the dx by say this as under root. So, I put it the d1 as this mod of xi1 minus eta 1 whole square mod of xi2 minus eta 2 whole square and so on plus mod of xin minus eta n whole square, where in this case x, xi1, xi2, xin by eta 1, eta 2, eta n, this belongs to Cn, where each xi are complex number, while in the first case x, which is xi I is 1 to n, y which is eta I, both are in Rn. Both are in Rn, that is they are reals, that is xi's are real, etas are real. Here they are complex number. Okay. So, that is why the modulus is used, so that this quantity becomes real and non-negative one. Now, as we have seen in R2, all the conditions are satisfied except the triangular inequality, which can be followed, which will be followed rarely with the help of the Minkowski inequality. So, that we could let know. Now, we have seen the metric on R2. Let us come back to this R2. The metric on R2D is defined as under root xi1 minus eta 1 whole square plus xi2 minus eta 2 whole square, where xi's are real, etas are real. Okay. Now, this is basically, these are the 2 points. This is the point xi1, xi2, here is the point eta 1, eta 2, and P is this point, Q is this. So, basically this is the distance PQ, okay, which is normally considered when we deal with the problem in the 2-dimensional plane. But whether this is the only way of defining the notion of the distance, because what is the distance function, what is the metric? Metric is a function from x cross x to R which satisfy those 4 properties. That is the property which we call it a axiom, metric axiom of the metric space, satisfy those properties. So, if we introduce the D in some other way such that all the 4 conditions are satisfied, then that new definition will also give a metric on the R2. For example, here if we define a metric on R2 as D1 x y equal to mod xi1 minus eta 1 plus mod xi2 minus eta 2. That is, what we are doing is we are taking the length PR plus RQ, and this sum we are saying is D1 x y, distance between x and y. This satisfy all the 4 properties. First thing, it is greater than or equal to 0. It is 0 only when this is 0, this is 0 means xi1 is eta 1, xi2 is eta 2. So, x equal to y and vice versa. It is non-negative, real, finite, and dx by is 0 if only x is 0. It is also symmetric x dxy is the same as d of yx, because this modular sign it will not affect if I interchange xi1 eta 1 and xi2 eta 2 they alone. Then fourth property, triangle inequality also follows if I add and subtract zeta 1 here and zeta 2 here. Suppose I take a point z which is another point zeta 1 and zeta 2, then what happen is when we take d of x by d1 of x by, then this will be equal to xi1 minus, I am just putting zeta 1 plus zeta 2, zeta 1 plus zeta 1 minus eta 1, and here I am adding and subtracting say zeta 2, and then apply that angle inequality modulus function. So, what we get is this is less than equal to this plus this, which is less than equal to mod of xi1 minus zeta 1 plus xi2 minus zeta 2 plus zeta 1 minus eta 1 plus zeta 2 minus eta 2, and that is equal to d1 of xz plus d1 of zy. So, triangle inequality is satisfied by this. Therefore, it also gives a metric on R2. So, R2 with this d1 is also a metric space. So, what we conclude is that on R2 we have two types of the matrix, that is one can define on X a metric in more than one way. So, only condition is that function which D, the way you are defining D must satisfy those four conditions, clear. So, it is not necessary that with a set X we have only one and only one metric, no, X is a set, one can define in so many ways the matrix on it. Okay. So, it is we get a different type of the metric space as soon as we change the notion of the distance on it. Okay. So, now till now we have discussed the set X where the elements either are real or complex number or maybe ordered pair, ordered n tuples and like this. But the functional analysis where we spoke is not only restricted only for the reals or complex. The X may contain the points where the points may be a functions, may be a sequences and something else also. So, the corresponding example for a metric space and which is very important and useful example is the sequence space L infinity. Now, here we take X, let X be the set of, let X be the set of all bounded sequences of real or complex numbers that is the set X is the set of all infinite sequences xi1, xi2, xi and so on, where xi's are either real or complex. This number real and complex such that the sequence xi is bounded such that mod of xij is less than equal to a constant m for every j. That is set of all infinite sequences which are bounded, that is each element of xi is less than equal to m. Since this bound will depend on x, so we also write this as mod of xij is less than equal to m suffix x for every j. So, x is the collection of all those infinite sequences which are bounded. This collection we denote this by L infinity. Hence, L infinity is basically is the set of all bounded sequences x xii I is 1 to infinity such that supremum of mod xii is finite over I. So, set of all bounded sequences, supremum means the if supremum is m, then all the terms of the sequence less than equal to m, and if we take a number slightly less than, then there are the terms which violate the condition that it will be greater than m minus epsilon. Okay, those terms. So, this is the definition L infinity. Now, on this L infinity, we define the distance distance as follows. Take the 2 point x and y and let us define the distance as supremum xii minus eta I over I. Supremum xii minus eta I over I, this, where x is xi I is 1 to infinity. So, it is a sequence of this type. Okay. In short, we write xi belongs to L infinity by which is eta I is 1 to infinity, this also belongs to L infinity, and we are introducing the notion of distance as follows. Now, this clearly satisfies all the conditions of the matrix. First is it is greater than equal to 0 because of the mod. It is a finite real quantity, non-negative. If it is 0, then supremum of this thing is 0 means the individual each term must be 0. So, individual each term means xii must be equal to eta I for each I. So, x must be equal to y, and conversely, if x equal to y, then xii must be equal to eta I for each I. Therefore, this supremum will be 0 and d will be 0. Then d of x y is the same as d of by x, because nothing to prove, just we are interchanging and mod of this is there. So, negative sign will be taken in care. Then d of x z is less than, or d of x y is less than equal to x z. So, let us consider z point which is suppose zeta I belongs to L infinity. Okay. So, consider this z equal to zeta I belongs to L infinity, and consider d of x y which is supremum of xii minus eta I over I. Now, if I add and subtract, then what happen is xi I minus zeta I plus zeta I minus eta I and take the supremum over I. This will be further less than equal to supremum of I xi minus zeta I plus supremum of mod of zeta I minus eta I. Now, this is again d of x z plus d of z y. So, triangle inequality is satisfied by this function. Therefore, L infinity under this metric D is a metric space. Is a metric space. Okay. And this is a very interesting metric space. Now, so far we seen the real numbers, complex number, then set of sequences. One of the example of the set of sequence we have seen L infinity. Now, see the function space. Now, here we take x function space, say CAB. What is CAB? Here we say CAB is taken as a set x, let x be the set of x means CAB, okay, be the set of all real valued function or CAB real valued functions x, comma y and so on, which are functions of independent real variable t and are defined and continuous on a given closed interval j. J. This set we denote by CAB. Just like a previous one, this entire set we denote this by L infinity. Similarly, this set we denote by CAB. So, CAB is the class of all functions x where the xt is continuous, well defined on the closed interval a b, set of all continuous functions which are defined on a closed interval a b. Now, over this CAB, we define the notion of the distance, define the distance function as follows. D of x by as the maximum of mod x t minus by t when t belongs to the closed interval a b, where the maximum denotes the maximum value of this difference over all t over the interval a. Now, first thing is whether this definition, this notion of the distance which we have defined is a well defined function or not, means whether it is a finite real value non negative quantity or not. Now, x and y both are continuous function over the closed interval a b, this is the interval a b, and functions x and y both are continuous and say x and y. So, we know that if f is a continuous function over the closed interval a b, then it attains its maximum and minimum value over the interval. So, over this interval a b, the function x as well as the function y will attain its maximum or minimum value. As well as we know the difference of the two continuous function is a continuous function. So, x minus y will also be a continuous function. Therefore, the maximum value will be attained by the function x minus y over the interval a b. Hence, this is well defined thing and it will be a some finite real quantity. Then second part is whether this is 0 implies x equal to y or not. If I take d of x y to be 0, then maximum of this thing is 0 for t belongs to j. T is varying over the closed interval a b. Now, when the difference of this is 0, maximum difference is 0, it means this is only possible when x and y are basically identical like this. Otherwise, the difference will not, maximum difference will not go to 0. If there is slight change in x and y value, the difference can never be 0. So, if x y is equal to 0 means the maximum difference is 0 means x and y must be identical, and vice versa, if x equal to y, obviously the d of x y will be 0. So, this satisfies the second condition also. Third one, it is symmetric in nature because of the modulus we won't lose anything if I interchange the x and y position. Then fourth is triangular inequality. So, to verify the triangular inequality, let us take the another function z in CAB and then find out this minus zt plus zt minus by t, and maximum is t over j. Now, it is less than or equal to maximum of this sum. Maximum is taken over j, t over t, t belongs to j, and like this. So, this is equal to d of x z and this one is equal to d of z y. So, what we see here is that this metric d, this notion of the distance function d over CAB satisfy all the condition of the metric condition axioms of the metric. Therefore, CAB under this metric is a metric space. Okay. Now, there is another way of defining the metric space on CAB. So, another metric definition on CAB. Suppose we define the function d of x by as a to b mod of x t minus by t dt. Then this is well defined thing where a and b function x and y both are continuous over a b, and since a b is closed. So, obviously, this function x t minus by t a to b dt, this will represents basically the area bounded by this function within the limit x equal to a, x equal to b and x axis. Okay. So, it is well defined thing and d of x y will be this. So, when you change x y, you are getting a different. Now, this is greater than or equal to 0 because this can never be a negative quantity. If it is 0, then either a equal to b or function must be identically 0. So, a cannot be equal to b. So, therefore, x t must be equal to y t, and vice versa. If x equal to y, then d of x y will be 0. Then d of x y is d of y x, and triangular inequality can also be shown that it is similarly. So, this forms a metric, and this is another way of defining metric on CAB. So, CAB one can define more than one way the metric here. Now, another examples are on the general sequence space S. Suppose we have the space S is the consist of the set of all the sequence space S consists of the set of all bounded, all unbounded, sequences of complex numbers and the metric d, which we define as, and d is defined as d of x y as sigma I is 1 to infinity 1 by 2 to the power I mod of x I minus eta I over 1 plus mod x I minus eta I. This is x I. Okay. So, this will be mod of x I minus eta I and this. So, I will repeat again, this is I is equal to 1 to infinity 1 by 2 I mod x I minus eta I 1 plus mod x I minus eta I. Now, the question is that whether this forms a metric, first well defined, and second one is why did not we use the same metric as we have used in case of the L infinity. For L infinity the sequence was bounded sequence. Therefore, if I take the supremum of mod x I eta I supremum of this, it may be unbounded. So, D may not be finite. Therefore, we cannot say dxy is the supremum mod x I minus eta I in this case. Okay. So, we have to take the definition in such a way, so that it should be finite, non-negative, real. Now, it is a valid definition. Why? Because this entire thing is less than equal to 1, less than 1. So, this entire series is dominated by 1 upon 2 I, sigma 1 upon 2 I. Therefore, sigma 1 upon 2 I is a convergent series, and we get the sum to be 1. Okay. So, this entire series converges and finite sum. Therefore, dxy is a finite, non-negative, real quantity. Further, dxy is 0, then this entire sum is 0. This is its absolute terms. So, individually each term must be 0. So, xi must be equal to eta I and vice versa if xi is there. So, x equal to y and y equal and so on. So, we get dxy is 0 implies x is equal to y and vice versa. Third is we can interchange the position of x and y, still there is no loss of generality, okay, because we can take the xi and eta I change. If I change, then because of the modular sign it is not effective. Then fourth inequality requires, triangular inequality requires to prove triangular inequality d of x y is less than or equal to d of x z plus d of z y, where z is zeta I belongs to say S. Okay. So, we write first an auxiliary relation. Let us consider a function f of t equal to t over 1 plus t. Okay. Let us consider this function t defined on R, t is in R. Okay. Then clearly derivative of this is positive, because derivative is nothing but 1 over 1 plus t whole square. So, this will be a positive quantity. So, function f is an increasing function, is an increasing. Therefore, the value of this a plus b, because we know a plus b is less than mod a plus mod b. Therefore, f of mod a plus b is less than or equal to f of mod a plus mod b, and this value if I replace this by t by mod a plus b, then we get mod a plus b over 1 plus mod a plus b is less than or equal to mod a plus mod b over 1 plus mod a plus mod b. Okay. And this will be further less than or equal to mod a over 1 plus mod a plus mod b over 1 plus mod b, because I am dropping here b, here a and this. Okay. So, we get this part. Now, from here it can be shown, if I take a to be, choose a to be xi I minus zeta I, okay, and b if I choose zeta I minus eta I, then a plus b, substitute in this a. So, put it in a, what we get is a plus b is mod of xi I minus eta I over 1 plus xi I minus eta I is less than or equal to mod xi I minus zeta I over 1 plus xi I minus zeta I plus mod of zeta I minus eta I over 1 plus zeta I minus eta I. Is it not? Using the a, this inequality, if I put a and b as suggested this, we get this. So, multiply by 1 upon 2 I and take the sum. So, we get 1 by 2 I mod xi minus eta I over 1 plus mod xi minus eta I is less than equal to 1 by 2 I mod xi minus zeta I 1 plus xi minus zeta I plus 1 by 2 I mod of zeta I minus eta I over 1 plus zeta I minus eta I. Okay. Take the summation I is equal to 1 to infinity, I is equal to 1 to infinity, I is equal to 1 to infinity. Now, because x is xi, z is zeta I, y is eta I. So, basically this will give the d of x y, and this is equal to d of x z and d of z y. So, this shows the triangular inequalities is also satisfied by this function. Therefore, S with this D is a metric space. Okay? This S with this. Now, this is not only the metric space, metric notion of the metric defined on S. One can go for another also metric, and thus another metric is that in place of 1 by 2 I, we can take mu I. We can take mu I. So, 1 upon 2 I can be replaced by mu I, where sigma mu I is finite, and rest will be thing. And the last example is a discrete metric space. Here we take x to be set of all points, and then notion of the distance x be the set of all points, x is the set of points, and define d as d of x y equal to 0 if x equal to y and 1 if x is not equal to y. Then this is a non-negative real valued finite quantity. It is 0 when dxy is 0, when if and only x is y. It is symmetric in x y, and triangular inequality also follows, because dxy is less than equal to d of x z plus d of z y. That is any point, if it coincides with x, then it is 0, but with y it will different, so we get the 1. Therefore, all the conditions of the matrix are satisfied by this. Hence, this metric x d is called as a metric space, and we call it as a discrete metric space. And this space is very much useful, particularly in establishing the counter, in giving the counter example. Thank you very much. Thanks. Okay.